Hello, everybody. So I'm going to get started. My name is Ethan Hooker. I'm an undergraduate student at the University of Cincinnati, and my research is over spin fractionalization in a quantum lattice superconductor heterostructure with Dr. Yashar Kamijani. So first thing is I'm going to go over what a quantum lattice is, which is something that most of you are probably very familiar with. But here we have a set of localized magnetic impurities or spins, and they are coupled antiferromagnetically to a sea of free conduction electrons. And these free conduction electrons, they are delocalized, so they can hop around with the effect of HT. And HK is the quantum term that accounts for this antiferromagnetic coupling. And then this is, in general, a difficult problem to solve. So from what follows, we will be looking at the strong quantum coupling limit. And here, JK is significantly larger than the bandwidth T. We find that the ground state, omega, is a tensor product state of singlets formed at every single site. So, what we can do is, in the strong quantum coupling limit, we can still introduce a small effect of the hopping term. And in this case, it can move an electron from one site to the other, and that creates a virtual doublon particle and leaves in its wake a virtual holon particle. These excitations, they are short-lived. They are both spin 1/2 and charge E relative to our singlet background. And in this process, the associated spins form a singlet state with one another. And if we want to see the effects of a doublon and holon on our lattice, we can, in principle, use neutron scattering. So if we have a neutron come in, it can scatter off of a conduction electron and entice a spin flip, and then that state would then become a triplet state. The cost relative to the background for that is 2J. And then if you look at this mathematical fact here, we know that both of these operators, when acting on our singlet state, give 0. So if we rearrange this, what it's telling us is that a spin flip triplet state can be regarded as a real doublon and holon particle pair at the same exact site. And then this doublon and holon pair can then propagate around the lattice as a free spin 1 magnon, and we will be looking at the dynamic spin susceptibility for this case. Note that if we do introduce a small hopping term, then this spin 1 magnon can fractionalize into a free doublon and a free holon particle, which can both separately move around and have effects on our combo lattice. The only issue is relative to the background. The energy cost for this is 3J, whereas this energy cost is 2J. So it's not an energetically favorable energetically favorable fractionalization. So we need to try and find some way to make this occur. We could consider accounting for the Coulomb potential between the doublon and the holon, and in that case, in the fractionalized state, this adds an energy of 2U. And we conclude that in order for this transition to be favorable, we would need a Coulomb attraction of less than minus J over 2 to get this doublon-holon fractionalization. The only issue is that both doublons and holons, they have the same charge, so this is not a physically achievable thing to do. Nonetheless, we can still look at the effects of having a doublon-holon pair on our singlet background. If we take our doublon-holon state and we act on it, our total Hamiltonian, we find a first quantized Schrodinger equation that governs the behavior of our two-particle wave function psi dh. And if we label our wave function with good quantum numbers k1 and k2, which represent the mixed momenta of our doublon and holon, we find that for large separations, this is the energy, and these correspond to free states where the doublon and the holon both can freely propagate around our lattice with no effect. Note that K1 and K2, they need not be purely real, and in the case that the relative momentum delta K has an imaginary component, this naturally leads to the bound state energy here. And the reason why that's a bound state is because if you look in terms of plane waves, we would be able to get exponential decay. So this bound state of a doublon holon pair can effectively propagate around our lattice, but the doublon and holon cannot move too far away from the other. So it's kind of like they're connected with a spring. So we find that the dynamic spin susceptibility for this case has this form if we define psi as our excitation energy here, and C is the matrix element given, and it's the coefficient of our wave function when the double and the hole they're at the same exact site. So here we draw plots of this, and we are running u from 0 to -1, and we are plotting the accessible states as a function of the total momentum q. You can see here the bound state for low u is more energetically favorable than our free states, but once u is pushed to -1, this situation flips. And if we have a Kondo lattice, it can naturally settle into a state with free doublons and holons for a sufficiently strong Coulomb attraction between the two. So our proposal is that we know that this attractive Coulomb term is not achievable, so the question is whether or not a superconductor could be used to replace it. Here the superconductor has this form, and if we bring a superconductor very close to our Kondo lattice, we can have Cooper pairs that tunnel into the lattice, and they transform doublon-holon states into doublon-doublon and holon-holon pairs. The good thing is that these doublon-doublon and holon-holon states, they are free, so they cannot form a bound state. So the question is whether or not these new free states can free up the energetically favorable doublon-holon bound state. And this can, in principle, be detected in an experiment like this, where we grow a Kondo lattice using molecular beam epitaxy, and we paint a very thin aluminum superconductor on top. It has to be sufficiently thin such that we can get neutrons to pass through it to entice spin flips in our Kondo lattice. So in order to add this superconducting term, it is convenient to write our Hamiltonian in this form using these definitions here, and you see that we get off diagonal elements in this smaller